And then we'll let it rip potato chip. Right. Here we go. Chemistry 3101. We've already made it to Chapter 2. Chapter 2, molecular representations. And in order to master organic chemistry, one must learn how to represent molecules a variety of ways, the most important being the bond line structure. And we're going to focus on that in the second section of this chapter. You also need to understand what are called the functional groups. So functional groups. And you hopefully saw that I posted a link to a YouTube video that I made a few semesters ago, wherein I cover all the different functional groups that you would need to know for this class. And again, I'll just write this down here. Bond line structure. Sometimes they're just called line structures, but I grew up calling them bond line structures. That's something that's also going to be very important for you in this chapter. Well, how do we represent a molecule? One of the first ways that you would have learned to represent molecules is by making a Lewis structure. Lewis structures were developed by Gilbert Lewis. And the great thing about Lewis structures is we can get a lot of information from them. However, they're really only useful for small molecules. And here we have a Lewis structure shown right here. This is what's called isopropanol. It's also known as rubbing alcohol. But the bottom line is that in the Lewis structure, we show every single bond explicitly. You can see every bond in the molecule is drawn out as a line. You draw in every lone pair. Everything is drawn out explicitly. But you can imagine that once you get into molecules that have, 10 or 30 or even 50 carbons, that drawing a Lewis structure can get rather cumbersome. They are very useful depending on the situation. And so how do we make them or simplify a Lewis structure a little bit? And what we can use is what's called a partially condensed structure. And since there are so many carbon hydrogen bonds found in organic compounds, what we do is we just eliminate any of the carbon hydrogen bonds. If you see a carbon hydrogen bond, you get rid of it. And you can see that in this partially condensed structure, they even got rid of the oxygen hydrogen bond. And actually, in fact, they didn't even get rid of this one. And so nothing more than getting rid of some of the bonds to condense the structure. And so we simplify it a little bit. Put another way, you can see how they grouped together this CH3 right here, and they grouped together this CH3 group over here, and then they grouped together the OH group right here. So partially condensed them, got rid of some of the single bonds to simplify the structure. And you can see how it would take much less time to write out the partially condensed structure than it did to draw the Lewis structure. Well, if you want to take that idea and extrapolate it, you can write out what's called a condensed structure, which is where we eliminate all single bonds. And when we can cluster or group a bunch of atoms together or groups together, we do that. Since we have two CH3 groups, we have the one in the blue circle and we have the one in the red circle, we can write CH3 and put the two of them in put it in brackets and then write a 2 over here as a subscript outside of the bracket, and that refers to the fact that there are two CH3s in the molecule. After that, they go over to the CH, which they've totally condensed. They put the carbon and the hydrogen next to each other, and then they have the OH all by itself at the very end, and that is this portion of the molecule right here. So that's an even more or greater, what would I say here, more condensed structure. So we've gone from the Lewis structure to partially condensed to fully condensed. And then something that you would definitely be used to from general chemistry is just a plain old molecular formula, C3H8O, because you would have used those all the time to do calculations of stoichiometry. You're trying to figure out how many moles of this and how many grams of that. You would have used molecular formulas all the time. The problem that can arise with molecular formulas in organic chemistry is you can't just look at this molecular formula and say, well, it must be this Lewis structure. Because in fact, there are several ways you can connect 3 carbons, 8 hydrogens, and an oxygen to make an organic compound. You could make the Lewis structure or a rubbing alcohol, which is what all these structures are, But you could also make this compound, so CH3, CH2, CH2OH. You could make that. That's called 1-propanol. And you could also make this compound, CH3O, CH2, CH3. They all have this same molecular formula. And so the molecular formula can be useful from time to time. However, it doesn't tell us anything about the way the atoms are connected in a molecule. So we have the Lewis structure, partially condensed and fully condensed in the molecular formula. One more thing I'll say about the partially condensed structure, this one right here, is that partially condensed structures will be used by your instructor. And if you like to watch YouTube and other people doing things, organic chemistry videos, you'll see partially condensed structures used from time to time, especially when an instructor like me wants to enhance a single bond. Like if they want the student to focus on one bond, they might condense everything except that one bond, just so the students will focus on the portion of the molecule we want you to look at. We're going to say, well, maybe that bond is the one that's reacting. And so that's where I find the utility of partially condensed structures really comes into its own. With all that information in mind, let's see if we can draw a Lewis structure from a condensed structure. And these are fully condensed structures. We'll start with B, it's 2.1b. And notice the first thing I see is that we've got a closed bracket here, or sorry, an open bracket and a closed bracket, and then we have a 2. So what that means is we've got two CH3CH2s attached to a CH. So what I'm going to do is I'm going to start by drawing out the CH. I'll put it like this, okay? And then I'm going to attach two CH3CH2s to it. So we'll put a CH2 and a CH3. Then I'll do another one, a CH2 and a CH3, like that. Then I have another CH2, so I'll put that over here, a CH2, and I'm going to show every bond because I'm drawing a Lewis structure. Then I have another CH2, put that one over here, CH2, and then I have an OH. Well, when I have an OH, that means the oxygen is going to have a bond to a carbon and to the hydrogen, because oxygen always has 2 bonds and 2 lone pairs. So we have our OH, and so we'll draw OH, we'll put the 2 lone pairs on the oxygen, and then hydrogen, like that. And there you go. There's our Lewis structure for the entire molecule. We took that completely condensed structure, and we were able to convert it into a Lewis structure. Give me a thumbs up if you follow me on that idea. If you have a question, let me know. We're going to try the next one. Okay, let's try the next one. In the next one, we have, let's see here. C, all right. So we've got how many CH2, CH3s? This time we have 3 of them, and they're all attached to one carbon with an OH attached directly to it. So let's start with the carbon. And that carbon is going to have 3 CH2, CH3s. So I'll go 1, 2, 3. So CH2, CH3. Oop, kind of running a space there. Let's see if I can move that a little bit. Oh, that didn't work, did it? There we go. Maybe move it over here. All right, so let's keep going here. We've got CH2, CH3. We do it again. Then we have the OH group. So we have the oxygen, 2 bonds, 2 lone pairs, and then the hydrogen. And there we go. We figured out the entire Lewis structure. Any questions about that? Don't hesitate to stop me if you have a question. Are there any questions about going from the condensed structure to the full Lewis structure? Can everybody hear me? Sorry, I'm not seeing anything on the chat and I'm reloading it. So, okay, great. Good. Thanks, everybody. Thanks, Andrew, Clinton, Nicole. Perfect. Sorry, I'm just always wary in case there's a lag or something and you can't hear me. Okay, so yeah, this is wonderful going from a condensed structure to a Lewis structure. But again, you can see how if you had to draw gigantic Lewis structures for molecules, it would get very cumbersome very quick. In fact, check this out. Here's a molecule I bet you that most people are familiar with. This is the Lewis structure of amoxicillin. And amoxicillin is a really cool molecule because it's an antibacterial that's used to treat many different bacterial infections. It's one of the most commonly prescribed antibiotics in children and costs just pennies per pill. I mean, somewhere between, it's probably about a nickel for a pill, maybe 5 cents for a pill or something. And what's cool about amoxicillin is it's a class of a compound called a beta-lactam. And this is beyond the scope of our course right now. But this part of the molecule right here, we call this a beta-lactam. We call this an alpha carbon, and then this is a beta carbon. It's got a nitrogen, so it's called a beta-lactam. And you could Google that if you want and find all kinds of cool information about beta-lactams. But what we're interested in is that even though amoxicillin isn't a humongous molecule, you can see how its Lewis structure is kind of complex. It would take a long time to write out. It says here, its condensed formulas would tell us very little about its shape, right? You see you've got a ring here, you've got another one here, another one here. And so in order to understand its shape, it's more effective to draw what's called a bond line structure. Check this out. Here's our Lewis structure on the top, and on the bottom, this is the bond line structure. Wow, this is much cleaner, very clean, and it's easy to see any heteroatom, meaning any atom that's not a carbon or a hydrogen. You can see this, nitrogen, oxygen, sulfur, oxygen, oxygen. And so your eye is drawn to what are called the functional groups. And thus, bond line, which are sometimes called skeletal structures, are much handier for organic chemists. And so what our next goal is to be able to learn how to draw a bond line structure of something like amoxicillin. Bond line structures, it says here, are the benchmark representations for organic compounds. It is critical to know how to draw these structures for any compound without difficulty in order to succeed in organic chemistry. You cannot, it would be impossible to pass this class without understanding bond line structures, okay? Everybody has to understand bond line structures. It's nothing that can be skipped. We're gonna get to that in a second, okay? Andrew, I see your question about, is there a hydrogen attached to a carbon or something? We're gonna address that in the next few minutes. Anyhow, again, if you look up any publication on organic chemistry, if you search any drug on Wikipedia and you Google the structure, it's always going to come up with a bond line structure like this. So let's see if we can figure out how a bond line structure works. And here's how you do it. It says each corner or endpoint represents a carbon atom. There's 6 carbon atoms in hexane or in 2-butene and 2-butyne. So this compound here, this is hexane. All right. You see that here we have a corner, or sometimes I call it a junction. Junction. Okay. Any corner represents a carbon. So this is a carbon. This is a carbon. This is a carbon. This is a carbon. And it also says that the end point represents a carbon. Therefore, this is a carbon and this is a carbon. So that means we have 6 carbons in the hexane molecule. Now, what did I tell you at the very beginning of this course? How many bonds does carbon have, generally speaking? Not a trick question. Can anybody tell me? How many bonds should a carbon have? Yeah, thanks, Nicole. It should have 4 bonds. If we look at carbon number 1, you see that it's only got 1 bond attached to it. Therefore, what that means is that it's inferred to the reader or to the looker or the viewer that there are 3 hydrogens attached to this carbon. We don't write them in, they're implied that they are there. If we go to the next carbon, carbon number 2, you can see that it's got 1, 2 bonds to it, but you've all just told me that carbon always has 4 bonds. Therefore, how many hydrogens are not shown that are implied on this carbon? Could anyone tell me? How many hydrogens are actually attached to that carbon number 2? Exactly. There are 2. Here's my blue pen. Here we go. There's 2 hydrogens here. We don't draw them in. They are implied. There's 2 here. There are 2 here. There are 2 here, because those are all junctions or corners, whatever you want to call it. And here at number 6, we end up at another endpoint. And so there must be 3 here because there's only 1 bond attached to that carbon. So here are all 6 of our carbons, 1, 2, 3, 4, 5, 6. And now we've gone ahead and drawn in all of the hydrogens. But you can see how if I take my pencil and I let it touch the page or the screen, how much faster it is to draw this compound. Watch. When my pencil touches the paper, that little dot that I just made, that's the first carbon. 1, 2, 3, 4, 5, 6, done. There you go. That's the entire hexane molecule. Now, if you're wondering, Mr. Dion, could you have started it up here? 1, 2, 3, 4, 5, 6. Would that represent the same thing? The answer is yes. If you're wondering, why did you draw it as a zigzag? 1, 2, 3, 4, 5, 6, like that. Well, the reason we draw like a zigzag, like Charlie Brown's shirt, is because it's accurate in representing the bond angles for sp3 and sp2 hybridized carbons. And since all of the carbons in hexane are all sp3, that's why we draw it as a zigzag. If you go to this compound here, this is 2-butene. We have an sp3 carbon and an sp3 carbon here. However, since this carbon has 1 pi bond attached to it, this is an sp2 hybridized carbon, and so is this. Right? We have 2 sp2 hybridized carbons, but again, we still draw the zigzag format for an sp2 hybridized carbon. Now, my question to you is this. If I zoom in on the 2-butene molecule, hopefully you can see that there are 1, 2, 3, 4 carbons. On carbon number 1, how many hydrogens are missing that are not drawn, that are implied to the viewer? Exactly. There's 3. 1, 2, 3. On carbon number 2, it has 1, 2, 3 bonds. How many hydrogens are missing that are implied on carbon 2? Exactly. There's 1 carbon implied here, 1 carbon here, and 3 carbons over here. So that would be our bond line structure for 2-butene. But again, if I just let my pencil touch the paper up here, and I start like this, 1, 2, 3, 4, and then put a double bond like that, that's much faster than drawing out the entire Lewis structure. When I have an sp hybridized carbon, sp hybridized carbons have linear geometry. And so I draw a linear geometry for an sp hybridized carbon. This carbon and this carbon, these are both sp hybridized. This one and this one are sp3. And so on the 2 carbons that are at endpoints, we know that there are 1, 2, 3 hydrogens here, and 1, 2, 3 hydrogens over here. How many hydrogens are missing on carbons 2 and 3? Could anybody tell me? Exactly, none. None. There's no hydrogen attached to this carbon nor this carbon. Why? Because they already both have 1, 2, 3, 4 bonds. So if they have 4 bonds, there's no point in adding anything else to it. But again, you can see how much faster it is to draw the bond line structure. 1, 2, 3, 4. Done. There's my bond line structure for 2-butene. And there you have it. So that's what a bond line structure is. Some more information that I have on this slide. It says the carbon atoms are not labeled, but a carbon is assumed at every corner or junction and every endpoint on the zigzag. The hydrogen atoms bonded to carbon are not drawn. We leave the hydrogens out in a bond line structure, at least the ones that are attached to carbon. We leave those out. So it says here, you must also be able to use the bond line structure language to interpret the number and location of hydrogen atoms in a molecule. Hydrogen atoms are not shown, but there's always assumed to be enough hydrogens to complete the octet of every carbon. If we look at this compound here, this is called 2-pentanone. If we just focus in on this carbon, again, and I'm repeating myself here, but this carbon has 1, 2 bonds attached to it. Therefore, it is implied that there are 2 more hydrogens attached to it that we don't show in the bond line structure, but they are there. Let me test you one more time. I guess this one's already done for you. Let's see. Let's move on down here. Let's try some practice. We already did this one. This is hexane. We already did it. But if I focus in on this compound right here, okay, this guy here, if I highlight this carbon in blue, I'll do this carbon in red, I'll do all the endpoints in red, and I'll do this one in green and this one in green. Could anybody tell me how many hydrogens are implied on the blue carbon but are not drawn in the bond line structure? Exactly. 1 hydrogen, yes. There's 1 hydrogen attached here. We don't put it in because it's a bond line structure. What about the red carbons? How many hydrogens are they missing? Yeah, absolutely. Absolutely. They're all missing 1, 2, 3. 1, 2, 3. 1, 2, 3. And then I think you're with me that the 2 green carbons are missing 2 hydrogens each because they both have 2 bonds directly attached to them. All right, now moving on a little bit faster, what you need to be able to do is to be able to look at a carbon like this and say, well, it's 3 bonds, so there should be 1 hydrogen here, 1 here. There needs to be 3 hydrogens here, 3 here, 3 here. I'm running out of space. And 3 here. All right, a little bit faster. And then if we look at this last compound here, you know, this one's a little bit more work because there's all kinds of interesting stuff in here. But let's try a few of these, okay? I'm going to erase these ones just to make room. I'm going to start with this carbon highlighted in blue. How many hydrogens are missing on this carbon? Exactly, only 1 because it's already got 3 bonds. And so there's a hydrogen missing here. Let's try this one here. How many hydrogens are missing on this red carbon here? Exactly, none. There shouldn't be any hydrogens on there, should there? Right, there's none there. There's none on this one. There's none on this one. There's none on this one. There's none on this one because all of those red carbons have 4 bonds. Okay, this blue carbon here, this one has 3 bonds, so it's missing 1 hydrogen atom. What if I put a green carbon here, here? You can see that both of those are missing 2 hydrogens. So they're both missing 2, like that. And then all the other ones, if I put a carbon here, 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 here. I missed one, didn't I? This one doesn't have any hydrogens attached to it. But all the ones that I have in black, those all have 3. So I'll just put CH3. I'll just condense it to save myself a little bit of time. Like that. Oh, I missed another one, didn't I? There's another one here. There we go. That doesn't have any hydrogens attached to it. Give me a thumbs up if you follow me on that idea. Bond line structure is pretty cool, huh? Just identifying the number of hydrogens. Great. Awesome. Awesome. Are there any questions about this question? Nice. Any questions about this one? Again, never hesitate to unmute your mic and just stop me. Not a big deal. I don't care. I love answering questions about organic chemistry. All right. There you go. I think if you understand this, you're in a good place right now. You should be like, you know what, I'm gonna go get another drink of coffee or something. You know, I'm having a good day. Because bond line structures, like it said, they're the benchmark. They're the most important thing you're gonna learn in terms of structures of compounds today. Just a few more rules. So one thing I've learned teaching science students, and I'm the same way, I'm still a science student, is that science students love rules. They say, you know what, Mr. Dion, give me the rules, I will apply those rules, and then I will get a good grade. And I don't think there's anything wrong with that mantra. I think it works rather well. But here are some rules. I don't think they're on page 54 anymore. This is an artifact from an old version of the textbook. We'll just put follow the rules. All right, so here we go. If you're given a Lewis structure or a condensed structure, you must also be able to draw the bond line structure and just follow the rules. So rule number one, whenever you have an sp2 or an sp3 hybridized carbon in a straight chain, like you do here, then it has to be drawn in the zigzag format. So we go from the chain to the zigzag, and it can be drawn the way it is here. If you draw it like this, it's the exact same thing. It's identical, okay? And if you're going, well, couldn't I draw it like this, 1, 2, 3, 4? Yeah, you could, but this is not as stable. It can exist, but there's a good reason behind doing the zigzag. You could do it like this, but that would just mean you're just being difficult, okay? We could just draw it going from left to right. Next rule is try to draw every bond as far apart as possible. You'll notice that I do that. I try to spread them out. So if you have this sp2 hybridized carbon here, remember that sp2 hybridized carbons are trigonal planar. And so in this bond line structure, you can clearly see that all the bond angles are around 120 degrees. But here, I mean, this looks like it's greater than 180. So greater than 180 equals bad. Okay, bad angle. Another great reason to buy a model kit is that if you make a hydrocarbon, meaning a compound made of only carbon and hydrogen, if you make a model of that compound, you're able to see how bonds can rotate. And so if you were to rotate this bond, it can put the CH3 group down here, and you could do the same thing with this bond. You could rotate it to put the CH3 down here, okay? And these are both identical to one another. What else? Heteroatoms, meaning atoms that aren't carbon and hydrogen. The ones that we run into the most are nitrogen, oxygen, sulfur, phosphorus. Now, we'll put X for halogens. Those will come up, halogens. Any heteroatom has to be drawn explicitly, and also the hydrogen that's attached to it. And then the cardinal rule, never draw more than 4 bonds to a carbon. If you ever do this, draw a carbon with 5 bonds to it, like this. There's a joke in organic chemistry. We call that the Texas carbon, and that is a big no-no. You never draw 5 bonds to a carbon. It's impossible. So going back to rule 2, it just says that whatever bonds you have, you try to draw them as far apart from each other as possible. Okay, so you see that this bond angle is way too small. This one is way too small. If you have 3 lines, what's the easiest or what's the farthest they can be separated? Like the way I have them drawn? No, you would put them at the all with a 120 bond angle, 120 degree bond angle, like this. All right, that's all it is. Just draw everything as far away from each other as possible. And those are the rules for bond line structures. Well, now that we've got bond line structures down, let's move on to identifying functional groups. Again, I have a YouTube video where I cover all the functional groups. And I posted an announcement about that this morning, so you can find that on my YouTube channel. In a functional group, it says a functional group is a characteristic group of atoms or bonds that possess a predictable chemical behavior. Wow, predictable. That means you can look at a molecule and based on its functional groups, you can predict how it's going to behave. When I was in graduate school, there was a professor who was an expert on a certain functional group. It was a functional group that contained sulfur in it. And this is just kind of an interesting story. He told me, or he told the whole class that I was taking that one time, let me go back here, that one time he was sitting in his office and somebody showed up that he didn't know. And the person was, carrying a briefcase, and he introduced himself and he said, "Hi, I'm a lawyer and I'd like to ask you, if I show you a molecule and show you, if I show you a functional group, could you tell me how you would think that that functional group would react? I know you're an expert in functional groups and especially in sulfur." And this professor said, "Sure, yeah, I can do that." So he showed him the molecule and he said, "What do you think would happen?" And the professor said, "Well, I think that this would happen. And my hypothesis is that this would happen." And the lawyer said, "I'd like to pay you $2,000 a day to be a witness in court for our company because, they're arguing that our compound is causing undesirable side effects, but you're an expert and you're saying that it's doing what we think it's doing." And he said, "Yes, I will accept the $2,000 a day to be a witness in court." And this is like 40 years ago or something. So pretty good gig. Anyhow, functional groups. Very important because it enables a chemist to look at a molecule and say, "Hey, this is going to react with water. It might cause an explosion or something." So there you go. The functional groups that you need to know are all the ones that are on this table here and the ones that I have on this slide as well. So that makes a total of, let's see here, 1, 2, 3, 4, 6. That's 12, 13, 14, 15, something around 15-ish functional groups. You don't need to know the names of the compounds. I think I even have that written here. Focus on the parts and right. Don't worry about the names because we learn nomenclature later on in the class. What you need to know, let me start here. You need to know that when you see a carbon with a triple bond to another carbon, that's called an alkyne. Okay, that's what you need to know. You don't have to know how to name 1-butene. That's something that we learn towards the end of this class. That's learned in chapter 9, which is over a month from now, so don't worry about that. But you need to know what an alkyne is. So anytime you have a triple bond between two carbons, you have an alkyne. Something that we've seen already today is when you have an OH group like this, and we saw that could participate in hydrogen bonding, that's called an alcohol. Anytime you have an OH group in a compound, that's called an alcohol. Now, let me address something here, and that is the R. You're wondering, what is R, Mr. Dion? I see R here and R here, but I look at my periodic table and there's no R. There's no R in my periodic table. Well, you're right, there is no R. What R stands for is this. It says R, it says it right here. R refers to the remainder of the compound, usually carbon and hydrogen atoms. So R is just some kind of group that's made out of only, or usually, just carbon and hydrogen. So if we go back here, and you might think, well, isn't water an alcohol then? Well, it's not. You might think, isn't H2O? Because that's got OH in it, yes, but H is not an R group because it's not made of carbon. The R group is normally made out of carbon. Not always, but most of the time. And so that's what an R group is. It's got to have carbon in it most of the time. All right, so we've covered alkyne and alcohol. The next one is an ether. If you have two R groups with an oxygen in between, that's called an ether. Here's an example. This is diethyl ether. This can be used to kidnap people. If you put it over somebody's face, they'll pass out. Anyhow, I wouldn't recommend doing that. But anyhow, that's an example of an ether. The next one is a thiol. A thiol is kind of like the sulfur version of an alcohol. You see an alcohol is OH. Well, a thiol is just SH. We don't deal with a lot of thiols in Organic Chemistry 1 because you see that these are covered in chapter 13 as are ethers and alcohols. I mean, that's Organic Chemistry 2, but you still have to be able to identify a thiol. The sulfur kind of version of an ether would be a sulfide. So you see that an ether is R and then an oxygen, then another R group. if you replace the oxygen with a sulfur, that's called a sulfide. And here's an example of diethyl sulfide. The next one is aromatic. Aromatic is kind of cool because you've got carbons alternating. You got 1, 2, 3, 4, 5, 6 carbons, and each one of them has a hydrogen attached to it, but only one because each carbon has a double bond attached to it too, or a pi bond. So they alternate, in an aromatic, it alternates double, single, double, single, double, single, and that is what an aromatic compound is. Benzene would be an example of an aromatic compound, benzene. And then they put here methylbenzene. This is called toluene. That's just the common name of this compound. So there's aromatics. Next is a carboxylic acid. If you took general chemistry 2, I'm sure you would have heard of this compound. So if you just have this is called acetic acid. Acetic acid, which is the acid found in vinegar. And acetic acid is a carboxylic acid. So you have an OH and a carbon with a double bond to an oxygen attached to an R group. So that's a carboxylic acid. The next one is an acyl halide. So an acyl halide is when you have a carbon with a double bond to an oxygen. Remember, there's a carbon here that's not shown because this is a bond line structure. And then you have X, and X can equal fluorine, chlorine, bromine, or iodine, because that's what the halogens are. So you can have an acyl halide. Here they show acetyl chloride. What's next? The anhydride. An anhydride is where you have 2 carbons that are doubly bound to oxygen and an oxygen in between the 2 of them, and 2 R groups like this. So this is an anhydride. A common one would be acetic anhydride. Next is an ester. If you like the smell of fruity things like strawberries and bananas and apples and oranges and grapes and any kind of juicy fruit gum, you can thank an ester, because esters like cherries and butter rum and oranges, well, I can keep going here, they have esters produce fruity smells. And so if you have a carbon doubly bound to an oxygen, single bond to an oxygen, and 2 R groups, then you have an ester. Notice there's a big difference between a carboxylic acid and an ester, right? In a carboxylic acid, you have a hydrogen attached to the oxygen here, but in an ester, you have an R group attached to the oxygen. Next, we have an amide and an amine. An amide is when we have a carbon with a double bond to an oxygen, and then it's got a nitrogen attached directly to that. The nitrogen can have R groups attached to it. And if you have an amine, this is when you just have a nitrogen with R groups attached to it. So no carbon with a double bond to oxygen. And the 3 last ones are if you have a double bond between 2 carbons, this is called an alkene. When you have a carbon with a double bond to oxygen and just 2 R groups attached to it, this is a ketone. And when you have a carbon with a double bond to oxygen, an R group, and an H, or a hydrogen, attached to the carbon, that's called an aldehyde. And I'm sure you've all heard of formaldehyde, okay, which is an aldehyde. So those are the functional groups that you need to know in this class. So let's start from the top. We got alkyne, alcohol, ether, thiol, sulfide, aromatic. Down here, we've got carboxylic acid, acyl halide, anhydride, ester, amide, amine, alkene, ketone, and aldehyde. So what I want you to do before the next class is practice the functional groups. And what we're going to do at the start of class on Thursday is we're going to start by looking at some compounds and seeing if we can identify functional groups. Let me just draw a compound just at random here, and we'll see if we can identify a functional group. Okay, so if I was to draw this compound like this, just move it over here like that. Could anybody identify a functional group in this compound? You might have to unmute your mic because I'm not sure everybody has the chat. Yeah, Luke says an amine. I agree. There's an amine right here. This would be an amine. Any other ones? Yeah, Kiana. Sorry, absolutely. There's an alcohol. Yes, alcohol. And there's one more. One more in here. So if we go, yes, absolutely. Not an easy one, but you all got it. So Coy, Tracy, and Kiana all got it. There's an ether here. Yeah, because remember that an ether is when you had an R, then an oxygen, then another R group. So you've got a carbon here, an oxygen, then another carbon. And so this counts. This would be an ether. Not easy. Okay, before I move on from here, I got one more thing to tell you about functional groups, and that is what's called a carbonyl. So a carbonyl, and you want to write this down, is when you have a carbon with a double bond to oxygen in it. Carbonyl, a carbonyl group is found in many functional groups. You can see that there's a carbonyl in an aldehyde. There's a carbonyl in a ketone. We scroll up, you can see that there's a carbonyl in an amide. There's a carbonyl in an ester. There's two carbonyls in an anhydride. There's a carbonyl in an acid halide, or sorry, an acyl halide. There's a carbonyl in a carboxylic acid. And so I want you to know that when I talk about a carbonyl, all I'm referring to is the carbon that's doubly bound to an oxygen. So a double bond to an oxygen. And that is what we call a carbonyl. All right, so now I won't have to just say carbon with a double bond to oxygen. When you hear me say the word carbonyl, you'll know that this is what I'm talking about. And carbonyls are found in lots of functional groups. Now, if you're sitting there and thinking, holy crap, that is a lot of things that I have to learn before quiz number 2, which isn't even all that, long from now. The answer is absolutely it is. Absolutely it is. There's a lot of work in memorizing all of the functional groups, but one thing I can promise you is that it is not in vain. Remember that these functional groups are going to show up in the rest of this class. They're going to show up in organic chemistry too. They're going to show up in biochemistry. And so whatever you learn about functional groups will never, ever, ever be a waste in this class. It will always come in handy. So now that we've covered functional groups, let's move on to formal charges. But before we do formal charges, I think what we'll do is I'll stop the video just so I can break it up into smaller chunks. So just bear with me for 1 second here. I'll just stop the recording and then we'll restart it. So stop. Yes.